Welcome to Newman Sixth Form Year 11 into Year 12 Taster Lesson for A-Level Further Mathematics. First, I'm going to show you a short video clip. Halfway through, I will start to explain some of the patterns that you see and how this links to some of our further mathematics topics. You may need to click on the arrow yourself to start the video. You can see the pattern that has appeared. As we zoom in, you can see these patterns reoccurring. They are identical in shape and form to the original pattern. This pattern will continue and continue to be produced. Some of the mathematics behind these, what we call fractals, link up to something that you've already met at GCSE, which is iteration, and something that you will learn in your first module at Further Maths, which is called complex numbers. Okay, I'm going to stop that there. Hopefully got your interest. There are lots and lots of these type of fractal patterns. This is the Mandelbrot set, something called the Juliet set, and I'll let you continue your research on that. So welcome to Newman 6 Further Maths. We are here to prepare, support and guide all students taking A-Level Mathematics and Further Mathematics at Cardinal Newman School. We hope to provide you with all the relevant information you require and give a helping hand to get you through the course. First, our expectations. The department and its teaching staff have high expectations of its mathematics students and as such provide high standards of teaching. Okay, let me introduce you to the members of the Key Stage 5 team. The following members of the department have experience teaching A and AS modules and are happy to help you. You can contact any of the teachers by email if you have any questions. Mr. Fanyo is our lead teacher for Key Stage 5. He's usually found in room 12A. Mr. Martin is our deputy head teacher. Mrs. Curtis, an assistant head teacher in room 25 usually. Mr. Ali is our head of maths and usually find him in room 11. Mrs. Streeter, our second in department, in room 16. Myself, Mrs. Bennett, I'm usually in room 14A. Miss Adzi, across the corridor from me, in room 13. Mr. Nagonga, in room 14, and Mr. Paparam, in room 10. Let me explain the course to you. So A-Level Further Mathematics is made up of 4 exam papers. The first paper studies Core Pure Mathematics 1. Paper 2 studies Core Pure Mathematics 2. Paper 3 covers Further Mathematics Option 1, which we've chosen to be Further Mechanics 1. And Paper 4 covers Further Mathematics Option 2, which is Decision Mathematics 1 for us. All of these papers are worth 25% of the overall exam, 90 minutes long for the exam, and each is worth 75 marks. So all papers have equal weighting. In Year 1, we would cover the textbooks for Paper 1 and Paper 4, so that's Core Pure Maths 1, and Decision Maths 1. In Year 2, we would cover the textbooks for Paper 2 and Paper 3, so that's Core Pure Maths 2 and Further Mechanics 1. All the exams for all 4 papers will be sat in May or June of Year 2. This is an example of our textbook. So we've got here the Core Pure Maths book 1, It says AS because they use the same textbook for AS, but our school just studies further maths at A level. And on the right-hand side here, we can see all of the topics that we're going to cover. And you can see chapter 1, I mentioned earlier, linked to that Mandelbrot set, we've got complex numbers there. And the Argand diagrams that go with that. Decision Maths is also a Year 1 module. That's the cover for the Decision Maths book, and the topics are on the right-hand side. A little bit later, we'll have a little introductory topic to Decision Maths. I've picked one of the topics to have a little bit of fun with later. In Core Pure 2, we have the topic list here. So there's probably things that you already recognise there. For instance, calculus, things to do with volume, obviously at a much higher level. Series. Further Mechanics 1. The list looks considerably shorter, but there's quite a lot of work in each chapter. So you may already recognise some of the topics there, things to do with momentum maybe. You may have heard of work, energy and power. Obviously there's a strong link between maths and science at this point. Okay, I thought it would be nice to show you another video clip here. Again, linking to core mathematics. You might have to click the video yourself to play it. I'm not sure if any of you have been lucky enough to witness the Northern Lights, the Aurora Borealis, if I can pronounce that properly, but a spectacular sight. Seen in the very far northern part of the hemisphere. Different colours, waves of cloud almost that move across the sky. Fantastic phenomenon. Again, mathematical understanding behind the workings of this, linked with science. Okay, I'm going to pause that there for us. So yet again, the Northern Lights and the way that they work, there's something to do with an electric particle and a magnetic particle, and that can be modelled using complex numbers. So again, a very close link there in the real world to core maths. Okay, I'm going to go through another couple of details with you. First of all, the transition from GCSE to A-level. How things progress from your studies so far at GCSE onto how things will look at A-level. Taking any A-level is dramatically different from GCSE. There is a whole emphasis on independent study. You may have called that homework in the past. Don't like to call it really homework, just homework at this level. Independent study is much more what it says it is, taking responsibility for your own learning, not just doing the bare minimum that you've been set for homework, but studying the topic in much more detail, practicing things that you haven't completed in class, revising, practicing. In other words, you have to do a lot more work in your own time to achieve the best you possibly can. And that's particularly true with maths and further maths. Data from the national benchmark clearly defines the minimum grade students should be aiming for relative to GCSE scores. It is important to have a realistic benchmark of your target grades. The minimum target grades the data suggests is as follows. So your GCSE grade that you achieve in maths this year compared to the target grade that you will be set for the end of year 2 at A level. If you achieve an 8 or 9, that's an old A star grade, then we would be expecting you to aim at a target grade of an A star or an A at A level. If you achieve a grade 7 at GCSE, then you'd be aiming at a B, C or D. Seems quite a wide range of grades there, but it also takes into consideration your average GCSE score. If you achieve a grade 6, that's an old grade B, then you would be looking at getting around a target of a D, E. I wouldn't say anybody would get a target of a U, but that's what you can be expecting around the lower end. And that's why we hesitate before accepting GCSE maths students with a grade 6 onto the A-level course. And Mr. Fanyo's favourite saying there, no pain, no gain. Students wishing to take A-level further maths at Cardinal Newman School must achieve at least a grade 8 or 9 for GCSE. Now that seems rather high, but bearing in mind that our standard A-level must also be chosen before you can study A-level at further maths, and we would insist on this being at least a 7. Further maths is much more complex, so we need the cream of the students, our highest achieving students for further mathematics. Students with a grade 7 may push to do the further maths alongside A-level maths, and Mr. Fanyo usually insists then on an entry test. And returning to expectations, in particular, we would expect you to attend all your lessons, arrive to lessons on time, be prepared to participate and work in lessons very hard, in fact, and be organised with your calculator, pens, pencils, rubber ruler, etc. Organise your work in a strong personal folder or file, with dividers preferably, and to bring your folder and notes to lessons. Folders are very often checked by your teachers. Okay, so studying both A-level maths and A-level further maths requires you to purchase a new calculator. This calculator has much more advanced functions. So the effective use of calculators is encouraged and expected in all units. The new Casio FX99 1EX calculator must be purchased by all in order to be successful at this level. So this calculator will cover you for both maths and further maths at A level. So why choose further maths? Well, first, it's diverse. There's something for everyone, lots of really interesting topics. Maths is one of the subjects that gives most options for degree choice, particularly with the Russell Group of universities. It helps increase earning potential by 10%. Most of us maths teachers and anybody that's really interested in maths will think it's awesome. It opens doors to a whole host of careers. It provides you with skills that will be useful for the rest of your life. And it will really force you to think. Lots of lateral thinking and problem-solving type questions in further maths. It can also act as a support to help improve your A-level maths grade. So now we've completed the introduction to the course, I think it's time that we had a small taster session from the Decision Mathematics 1 course. we're going to have a look at something called the Seven Bridges of Königsberg problem. Before we look at this in more detail and the history behind it, we need to do some basic maths. Okay, so we're going to have a look at some doodles. Most of you will know what I mean by a doodle. Some of you have your own favourite doodles that you might do while you're daydreaming, maybe chatting on your phone. And what we're going to do is we're going to try drawing each of the doodles below without removing your pencil from the paper and without retracing a line that you've already drawn. Which ones can be drawn? Now you can pause the PowerPoint using the three dots at the bottom of the screen, and then when you're ready, you can resume playing the PowerPoint. I'm going to show you the first couple, just to make it clear what I mean. So using a highlighter, if I start at this corner, and in fact on this first shape, it doesn't matter which corner I start on, I can trace the shape without taking the highlighter off the paper. If I do the next shape, I'm going to start here, I might start highlighting, and depending on when you start from, sometimes it doesn't work. Here I've had to then lift my highlighter off the page in order to complete that. So, doesn't mean to say it can't be done. Just going to erase that and just show you that in fact if I start from this corner, I can go round here, up here, and in fact there's different options to do, but that shape can be traced. Okay, so if you want to pause the PowerPoint and have a little ponder on the next few shapes, and click resume when you're ready. Okay, so looking at this again, we can see the first shape worked. And the second shape also worked. Just going to show you a demonstration of that again. The third shape, however, does not work. Hopefully you didn't think that one worked. So you can't doodle that shape without taking your pen off the paper. The next one is my favourite one, and that one works. Just show you. There's actually two positions that you can start that doodle and it still work. The next shape also works. I'll just show the evidence of that. And the next shape also works. Here we go. And the last shape does not work. Now what we're going to aim to do is to try and use our understanding of what's happening with the diagrams in order to be able to predict when a shape can be doodled and when it can't be doodled. Now we're only looking at shapes really with some vertices. It doesn't have to be straight lines. We will also consider shapes. This works on shapes with arcs drawn between the vertices of the shape as well. So the doodles below are strongly related to the problem of the seven bridges of Königsberg. Once you understand the solution to this problem, you'll be able to tell whether or not any doodle can be drawn, no matter how complex it looks. You can see the one to the right of our shapes there looking very, very complex. We've got a number of vertices. Just use the highlighter here. Number of vertices. These are the vertices. And what we call edges. So we've got edges that are arcs and edges that are straight here. Okay, let's look at the history of the 7 bridges of Königsberg problem. Leonhard Euler, seen on the left there in the photograph, was a Swiss mathematician whose power of mental calculation was prodigious. As a teenager, his fame quickly spread throughout Europe, and at the age of 20, he was summoned by Catherine I of Russia to study at the Academy of Science at St. Petersburg. He became Professor of Physics at 23 and Professor of Mathematics at 26. At the Academy, he contributed to numerous branches of mathematics and other sciences, including work on optics and the study of planetary motion. He made progress towards solving Fermat's last theorem and introduced the notation for pi, which you already know about, and sigma, which you may have seen on spreadsheets. At 31, he lost the sight in his right eye and later became almost totally blind. He had 13 children, of whom only 5 survived their infancy. His life's work of 886 books, papers, was still being published 50 years after his death. And it was Leonhard Euler that was responsible for the solution of the 7 bridges of Königsberg problem. Whilst working at the Academy, Euler got to hear of the problem of the 7 bridges of Königsberg. The River Pregel ran through the town and divided it into 4 land areas, one of which was an island in the middle. The river was spanned by 7 bridges, and the people of the town tried to walk a route around the centre that crossed all 7 bridges once and only once, a bit like our doodles. We're going to use the next page to try and find a route around the centre, crossing all 7 bridges once and only once. You can start your journey from any point in the town, and you can finish at any point. Okay, back to the 7 bridges map, if you will call it a map. So we can see here that we've got the different land areas. Okay, here are the different land areas, one at the top, one at the bottom, one in the middle, and one at the side. And this is the River Pregel running and separating the town. Here are the bridges. We've got 1, 2, 3, 4, 5, 6, 7, hence the name, the 7 bridges of Königsberg. Imagine you start at the top region. You can cross each bridge exactly once, and you should be able to finish in any region. You don't have to get back where you started. Pause the PowerPoint and see if you can imagine completing this problem. When you're ready, resume the PowerPoint to find out if it's possible. Okay, a little demonstration for you. Starting at the top region, you can see that this is not possible. We've only crossed 6 out of the 7 bridges and ended up in the region on the right-hand side. I'm not sure how many different regions you'd have found, but it is in fact impossible to cross each bridge exactly once. A little saying just appeared down on the left. I think we need another bridge, Becky. Okay, let's have a little look at why this is. Starting at any vertex, use a pencil. Ideally, I had a worksheet for you to use here. Do the best that you can with some of these answers on the screen to determine whether or not the networks below, we call the diagrams with the nodes and the edges networks. And we're going to decide whether they're traceable or not. Use the table provided to complete details on the number of odd and even vertices. I'll explain that in a minute, contained in each network. Use your results to predict the traceability of any network. So you can see question A has already been complete in the table. So So the column for the number of odd vertices, there are 2 vertices of odd degree. We call it odd degree. So if we go over to the diagram for A, if you count the number of edges connecting to this vertex, there's 1, 2, 3. That's an odd number of edges connecting to that vertex. There's also one more vertex with 3 edges connecting to it. So this diagram has 2 odd vertices. The other 2 are even because there's an even number. There are 2 edges connecting to this vertex and 2 edges connecting to this vertex. So that's 2 vertices with odd degree, 2 vertices with even degree. So we've got 2 and 2. Is it traceable? Well, you'll have to go over the top. I think we did this one earlier. And I think if we start here, then we should be okay. I'll just get the pen and check. Starting here, going over the top, we can trace it without lifting the pen over the paper. So that's yes. Then the second shape, we have B, count the number of edges touching each vertex. You could write this on the diagram, it might help. 3 there, we've got 3 there, 3 edges touching this vertex, and 3 edges touching the central vertex there. So that's all odd vertices. In fact, there are 4 odd vertices for that diagram. There are no even vertices, no vertices of even degree. And if you try and trace that, doesn't matter where you start, I'll just show you a quick example. I've got here, I'm going to end up there. And I would have to lift my pen off the paper, and that will happen wherever you start. So my suggestion is, if you want to have a try at a couple of these, ideally what we would do is fill in the whole table, have a go at a couple of those, and then we'll reveal the answers and have a look at how the answers connect up with the traceability. So it's down to the numbers that we're getting linked to whether we've got odd vertices or even vertices to the answer of whether it's traceable or not. Pause the PowerPoint and have a try at some. Okay, and the answers are all going to appear at once. So here we've got the answers for all of the shapes. So looking at what we've achieved here, we should start to be able to find a link between the answers that say yes. So the first one was yes, we had 2 odds, 2 evens. The third one here is yes, we've got 0 odds and 4 evens. The next one to say yes is shape E with 0 odds and 3 evens. If you start looking at the connections between the numbers that we get for the number of odd and even vertices and the answer's yes, we should see a pattern. Okay, so we can now see that all of the networks that are traceable have been highlighted in the table. Notice that the only values that are highlighted are the odd vertice column and the traceable, whether they're traceable or not. So we're interested in all the ones that are traceable. The reason that we haven't highlighted the values in the number of even vertices column is because they vary so much. So shape A has 2 even vertices, shape C 4, shape E 3. So some of them are even numbers, some of them are odd numbers, very high numbers. And this does not have any bearing over whether the network is traceable. So looking more at the number of odd vertices column, we can see that the numbers start to have some sort of meaning. We've got 2 odd vertices in the first diagram, and it's traceable. In diagram C, we've got 0 odd vertices, and it's also traceable. Shape E has 0 odd vertices, it's also traceable. Shape G2, shape J2, shape L2, and shape N0. all of the other shapes with different amounts of odd vertices are not traceable. So there's definitely a pattern here. Hopefully you can spot what it is. And in fact, a network is traceable when the number of odd vertices it contains is either 2 or 0. Hopefully you spotted that. Euler proved that a network is traceable only when it contains exactly 2 odd vertices, or if all its vertices are even. And what we need to do now is to look at how he used this to solve the 7 bridges problem. So we should be able to use Euler's result and network K to explain the answer to the 7 bridges problem. This diagram represents what we saw in the 7 bridges problem. We have 3 land masses here, one in the centre, one above, one below, and a fourth to the right-hand side. And there are 7 bridges connecting each of these, represented by the edges or arcs here. If we try and trace that by doing what we were doing, doodling it, going over the top, then we should find that it's not traceable. And I come stuck there. Okay, if we get rid of that and count the vertices, the degree at each of the vertices, we've got a link hopefully to what we just found out. 1, 2, 3 here. 1, 2, 3, 4, 5 here. This vertex has degree 3 and the bottom vertex 1, 2, 3 again. And what do we notice? That the 7 bridges problem has all vertices of odd degree. It's got 4 vertices of odd degree. And that means that we can't trace it. Okay, so that hopefully summarises why that 7 bridges problem doesn't work. We should be able to use network L next to it to explain what would happen if an 8th bridge was built. You can see here an extra bridge has been put on in the 2 centre bridges, going across from here to here. If we now count the degree, we've got 3 still here. 1, 2, 3, 4, 5, 6 here, so there's a degree of 6 there. 3 here, and on the right-hand side, 1, 2, 3, 4. We now have the requirement. We've got 2 even ones. We can have as many even vertices as we want, but we have the requirement of 2 odd vertices. So either 2 or 0 odd vertices will work. And we should be able to just go over the top of that and show its traceability. Nearly there. And there we go. Okay. So although the people of the town felt that such a journey was impossible, they couldn't actually prove it. Euler tackled the problem for them, and he decided that he didn't need to make the journey to Königsberg. Instead, he abstracted the problem and made a sketch of the situation. Euler represented the land areas by lettered vertices and the bridges by arcs. The resulting diagram he called a network. So Euler was actually responsible for starting this work on graphs and networks that we study in Decision Maths 1. Euler undertook a study of general networks and was able to determine the conditions under which a network was traceable. That is, the network could be fully traced by passing along all arcs once and only once. This equivalent to drawing the network on paper without lifting your pencil or going over a line once drawn. And to finish off now, we really should look at the amended problem. The title has now changed to the 8 bridges of Königsberg. And we can see the 8th bridge has been drawn over towards the right-hand side, where we only had 1 bridge here. We've now got 2 bridges. So we now have a total of 8 bridges, still the same original land masses of 4. There are only 2 positions that we can start or finish on this particular network. So if you think in terms of the degree of the vertex at the top, it leads to 1, 2, 3 bridges, so that would be degree 3. At the bottom, we would have 1, 2, 3. In the middle, we would have 1, 2, 3, 4, 5, 6, so that's even. And over on the right-hand side, 1, 2, 3, 4. So there's an extra added complexity with networks and graphs that we haven't really looked into, and that's where you're allowed to start and finish. So I'm just going to let you have that last piece of information. If the graph is semi-traversable, then you've got exactly 2 nodes that have odd degree, which is what we have here. You have to start and finish at those odd nodes in order to make this traversable. So we can either start at the top or at the bottom, but we wouldn't be able to start in the middle or on the right-hand side. We'd need further bridges added to be able to make that possible. Okay, let's see a demonstration of that. And here we go. This is known as a semi-traversable network because we start and finish in different positions. And that solves the 7 bridges of Königsberg, which is now the 8 bridges of Königsberg. Okay, so that's one brief insight into a topic that we do in decision maths. That then goes on to other algorithms that we'll study within the same chapter. And I'll just remind you of what I said earlier, that you're more than welcome to email any of the teachers that teach A-level maths on the previous slide. So don't hesitate. If you've got any questions at all, please contact us. It's been a pleasure explaining what further maths would be like at Cardinal Newman, and it's bye from me.